second lecture of module 2. That means today we will continue our discussion on the heat transfer through extended surfaces or the heat transfer through rectangular fins. So in the previous lecture we had seen that how the heat transfer rate can be increased by using or attaching the extended surfaces by increasing the net surface area. So we had applied the basic temperature distribution equation for the infinitely long fin, and we had informed that we had mentioned that we shall take two other different cases or two other practical cases, and we will find out how the general equation of temperature distribution can change according to the boundary conditions. So today we shall take two specific conditions, and we will take two numerical problems regarding. But here please note on the third point where we have mentioned that today we shall discuss the different cases of heat transfer through rectangular fins depending on the different boundary condition, that is finite length of fin with insulated tip and heat dissipation in form of convection from the tip. Okay, so these are the two basic things that we shall discuss today, and I hope that you will be able to analyze this specific two cases, and you will be able to differentiate between these two so that it can help you understand the practical problems regarding the heat transfer through extended surfaces. Now these are the lecture outcomes here. So it is almost same. There is a only change in the boundary conditions, so we will not waste. So we will start discussing regarding the temperature distribution and heat transfer for fins with finite length and insulated tip. That in the previous lecture we had discussed uh, that the fin has an infinite length and there is no insulation at the tip. Okay, so today we shall take a specific case where the boundary conditions is defined by this insulated type condition and this fin has a finite length. So here this diagram obviously refers to the infinitely long fin, but we will not move on to that factor, but we will just do a little bit of recapitulation thing so that the working principle of any kind of fin can be discussed once again, so that the working principle can be remembered by you guys. Okay, so what happens in a fin? This is your base area, and you can see a fin is attached over here, and we have taken a little bit of area or a sectional area so that we can analyze on this factor. So if this is our sectional area, then you can understand that this amount of heat qx dot to be specific is entering this section and it is leaving at qx plus dx, where dx is the thickness of the section. Now the question is here you can see a little bit of wavy lines that indicates that the heat is getting transferred via convection. So you can see that this is the only surface from which the conduction is taking place, but you can say this overall surface, and you can also understand that in this surface heat transfer, or for this surface and the opposite surface to this one, heat transfer is taking place via the mode of convection. So here this is convection, this is convection. Okay, so heat transfer is taking through the mode of convection in four directions in this okay, so in this direction, the direction opposite to this plane, that is hidden over here, and again heat is getting transferred via convection from this plane and the plane opposite to this. So you can see the net surface area of convection heat transfer is getting increased hugely, so that increases the heat transfer rate. Okay, so this is the working principle of any fin. Now in our previous lecture we had taken an infinitely long fin but today we shall take a fin which has a length of L. So this is our fin which has a length of L, and this fin is insulated at the tip. That means there is no heat transfer going out in the outer direction from this fin. So we know the initial boundary condition that we have already mentioned in the previous lecture, that the first boundary condition will remain same for any cases of fin. Only the second boundary condition will go on changing depending on the nature of the fin, okay, or the length of the fin or the heat transfer at the tip. Okay, so if you remember the first case, theta is equal to theta b at x equal to 0, right? That means at base theta is equal to theta b. Okay, so at base the temperature difference is Tb minus T infinite, where Tb refers to the base temperature and T infinite refers to the surroundings temperature. So we found the initial boundary condition as theta b equal to C1 plus C2. So this is our initial boundary condition, which will remain fixed for all cases of fins which we'll analyze. Okay, so theta b is equal to C1 plus C2. And now let us concentrate on this condition. That means this fin has a finite length and it is insulated at the tip. Okay, that means it is quite easy to understand that at this length, at the end of this fin, so at x equal to L, at x equal to L, it is quite understandable that this temperature gradient would become 0. Okay, so this temperature gradient would become 0 because the tip is insulated, so there will be no temperature gradient present, and at x equal to L, or the end point of the or the end length of the fin, the gradient would be 0. So if you just derive this equation, the equation which we had derived like this, if you remember, the general equation of temperature distribution, which goes on changing depending on the boundary conditions. So C1 into e to the power mx plus C2 minus e to the power minus mx. Okay, so this is our general temperature distribution equation, which for m was taken as root over of Hp by Ka, where H is the convection heat transfer coefficient, P is the perimeter of the surfaces from which the convection is going on, K is the thermal conductivity of the fin material, AF is the area over which this heat transfer is, or specifically to say AF is the fin area. Okay, so now at x equal to L, dt dx is equal to 0. So if we derive or differentiate this equation, we'll find that so it will be better that if we write this thing at x equal to L, dt dx x equal to L is 0. So if we differentiate this equation, we'll find that m, okay, so I'll just write down the differentiation part. So here we can see that after differentiating this equation, we'll find that this dt dx would become, we know that theta is t minus t infinite, so when we are differentiating this equation with respect to x, then dt dx becomes m into c1 into e to the power mx minus mc2 into e to the power minus mx. So now you can easily understand that this m is common in both this equation, so we can simply remove this m from both the equations, and we are left with this equation. And now if we do a little bit of rearrangement, then we can understand that this is our solution, or this is our final equation. So what happens if we try to write C1 in terms of C2? So it will become minus 2mx. Okay, so it will become C2 into minus e to the power minus 2mx. Now remember, we had differentiated this equation at x equal to L, so we can put this L here, or you can also put this x equal to L in the previous steps also. So this would become e to the power minus 2ml. So C1 is equal to C2 into e to the power minus 2ml, and C1 plus C2 is equal to theta b. So now you have two separate equations of C1 and C2, and from these two equations you can find out the values of C1 and C2. So I will not go on with the calculations, and I will just write the final equation. It's your responsibility, or it's your part to do these calculations, to these necessary calculations, so that you can be reaching at the same values. Okay, so theta b into, okay, I will just write the terms here. So after doing the relevant calculations, you will find that C1 would become theta b into e to the power minus ml divided by e to the power ml plus e to the power minus ml, whereas C2 will be like this. Now we know the basic equation, C1 into e to the, we know the basic equation, that is C1 into e to the power mx plus C2 into e to the power minus mx. So this is our final form, and this can be rearranged in a different way, and a new function would generate from this arrangement, and I will discuss about this new function and this rearrangement kind of thing. So we can see that this function of theta can be rearranged like this: theta b into e to the power m into L minus x plus e to the power minus m into L minus x. Okay, so now let us introduce the hyperbolic function, or cos hyperbolic. Suppose we want to find out the cos hyperbolic function of x, then it would simply mean e to the power x, that is exponential of x plus exponential of minus x divided by 2. So this is our cos hyperbolic function. Okay, now if you want to find out the sine hyperbolic, then it will be almost similar to that of cos, but only there will be a minus here. So it will be e to the power x minus e to the power minus x divided by 2. So these hyperbolic functions can be included here, because you can treat this function as e to the power x. So let us consider this as our x, and this is our minus x. Similarly, x and minus x. So from basic understanding of mathematics, we can say that we can define this function or rearrange this function in such a way so that we can write theta is equal to theta b into cos, okay, just I will do it. So cos hyperbolic of m, okay, so it will be m into L minus x, okay, and divided by cos hyperbolic ml. Okay, so this is our final arrangement, and you can also write this as theta by theta b. Okay, so you can understand this fact that the temperature distribution for fins having finite length and insulated teeth, the temperature distribution can be written according to this formula. So we will write down the final temperature distribution we which we have generated for this type of fins. Okay, so now I will just write down the final formula. So the temperature distribution can be written in this formula, where T is the temperature at a distance of x, and T infinite is the temperature of the surroundings, which we have written as theta. T minus T infinite is treated as theta, and Tb minus T infinite is treated as theta b. So it can be written as cos hyperbolic of m into n minus x divided by cos hyperbolic of ml. So now if you want to find out the heat transfer, that means heat at the base, so x equal to 0. If we want to find out the heat transfer, so x will be taken as 0. That means we are trying to find out the heat transfer at this base from where the fin is attached. Okay, so it will be simple. We'll be using this simple formula of Fourier's law, and I will just do the calculations. Okay, so when we are trying to calculate the heat transfer rate, here you can see from Fourier's law, minus k into AF, the area of the fin, into dt dx at x equal to 0. So when we are interested to find out this dt dx at x equal to 0, we find that it becomes minus tb minus of tb minus t infinite into m into tan hyperbolic of ml. Okay, so this value is found out after putting x equal to 0, and when we put this dt dx at this equation, we get this as our result. So this is the heat transfer rate, and this is our temperature distribution. So we will use these two formulas. A very we'll be using these formulas so that we can solve the different numerical problems. So, but I would like to tell you one thing. Suppose there are two extra fins attached from this. So if you are asked to find out the heat transfer rate from the finned and the unfinned surface, then how you can calculate it? The basic point depends on the area. So that means this area, this base area should be, or specifically to, I would say that this area should be removed from this one and this one. Okay, so that you get the area which is unfinned. Okay, that means there is no fin attached to the area. So I think you will be able to find out this area, and then you just apply the laws of convection so that you can find out the heat transfer rate. That is as simple as it is. Okay, so with this understanding, let us take another problem. Okay, sorry, let us move on to the another boundary conditions, and let us see how we can apply the same thing for the second boundary condition. Okay, so now we shall discuss about another case where the fin is losing heat by convection at the tip. In the previous case, we had seen the fin was insulated, but here the fin is not insulated, and there is heat transfer in the form of convection going on with the surroundings. Okay, so at steady state conditions, the heat which is being conducted, that will be equal to the heat which is being convected. Okay, so at steady state conditions, the convected heat is equal to the conducted heat. Okay, so from this equation we can form the second boundary condition. The first boundary condition is already predefined and which is constant for all the different cases. So this is our first condition, and from this equation we can generate the second boundary condition. Okay, so since this AF is common in both the cases, we can remove it, and we can find that there is a relationship between the C1 and C2. If we derive this, if we differentiate this equation, then we'll certainly find a relationship between C1 and C2. So this calculation should be done by yourself so that you can arrive at the solution. And after, so I am, it is a little bit of tedious calculation that cannot be shown in this through this video lectures, because it would take a very much time. So I'm avoiding these tedious calculations, but it is a task to you to do the calculations by your own, so that you can understand how this relationship can be reached. That means the theta by theta b, that is t minus t infinite divided by tb minus t infinite, is the hyperbolic cos hyperbolic of m into l plus l minus x plus h by mk into sine hyperbolic of m l minus x, okay, divided by cos hyperbolic function of ml plus h by mk sine hyperbolic of ml. Okay, so this is the temperature distribution. It can be written in this format also: T, that is T minus T infinite divided by TB minus T infinite. Okay, so this can be also written in this format also. Okay, so this is our temperature distribution for the fin, which is having a finite length but it is not insulated. So at the tip of the fin there is heat transfer going on via conduction as well as convection. So the heat which is conducted through this material of this fin is exactly equal to the heat which is convected with the surroundings. So at steady state conditions, this convective heat loss becomes equal to this conducted heat. Okay, so here we can see that from this equation we can set up a relationship between C1 and C2, and from this first equation and the second equation, which should be generated from this equation, from these two equations we can find these values of C1 and C2. Okay, so and after finding this C1 and C2 we can follow up this typical relationship C1 into e to the power mx. So the values which we obtain for C1 and C2 needs to be calculated here or put here, so that we can reach at this temperature distribution equation. And this is the heat transfer rate which should be generated from this equation only, and it becomes at the base. Obviously we are calculating the heat transfer at the base as sine hyperbolic of ml plus h by mk cos hyperbolic of ml divided by cos hyperbolic of ml plus h by mk sine hyperbolic of ml. So these are the two basic formulas for the fin which is not insulated and there is convective heat loss at the tip. So with this we have discussed three type of boundary conditions. The first one being the infinitely long fin. The second two conditions were for finite length, but in the first case we had seen the tip of the fin was insulated, and in the second case we have seen that there is convective heat loss going away from the tip of the fin. Okay, so with this understanding, or to be specific, with the two understanding that we have understood from this lecture, we shall take two different numerical problems which resembles to this understanding, and we will see how these concepts can be used to solve numerical problems. So let us see our first problem. A heating unit is made in the form of a vertical tube of 50 mm outside diameter and 1.2 meter height. The tube is fitted with 20 steel fins of rectangular section with height 40 mm and thickness 2.5 mm. The temperature at the base of the fin is 75 degrees Celsius. This degree is not given here, somehow it is missed. The surrounding air temperature is 20 degrees Celsius, and the heat transfer coefficient between the fin as well as the tube surface and the surrounding air is 9.5 watt per meter square Kelvin. if the thermal conductivity of the fin material is 55 watt per meter Kelvin, make calculations for the amount of heat transferred from the tube with fin and without fin. Okay, so this is our question here. So here I have drawn a case of rectangular fin, but please consider that in this problem it is not a rectangular fin. But to make yourself understand regarding the area of unfinned surface and the finned surface, I have drawn this, which can be always implicated to the cases of cylindrical fins also. Okay, so let us start with the problem. You have to calculate the amount of heat transferred from the tube with fin and without fin. So let us first start with the calculations of heat flow without fin. So if there was no fin present here, then this total area would have been your heat transfer area, and there would have been convection taking place between this outer surface area and the surroundings, which is kept at 20 degrees Celsius. So we follow the simple rule of convection. We know the formula of convection heat transfer according to Newton's law of convection, and that is H into A into delta T. So this was your base. That means the base was maintained at temperature 75 degrees Celsius. So 75 minus 20, TV minus T infinite. H is given as 9.5, so we put 9.5, and the question is about this area. So since this is a cylindrical area, and we know the heat transfer is taking place through the lateral surfaces only, and this is convection, mind it. So when we are considering the lateral surfaces of a cylinder, then the area would become 2 pi r0h. Okay, r0 signifies the outside radius. Now you know that 2r0 means d or d0 or the diameter. So you have simply written pi d0 l or h. H refers to the height, or sometimes it can be also referring to the length. So 2 pi r0l or pi d0l. So this is the area, simple area of the surface from which heat transfer, convective heat transfer, is taking place if there was no fin present, and we find this data to be calculated as 98.44 watts. Okay, so now we have found the data of heat flow without fin, and that has come as 98.44 watts. So now let us try to find out what will be the heat transferred from the tube with the fins. So now we have to consider that this fin is insulated at the tip. Okay, this fin is insulated at the tip. So if the fin is insulated at the tip, then what is the basic formula to calculate this? I will write it so it can be easily remembered. So now you need to understand the special case here. So when a fin is attached to this base, this is the area, or you can say this is the area of base which remains unfinned. Okay, so here you can see that there are 20 steel fins. So the area which remains unfinned between these attached fins, we need to calculate that area, because heat transfer is taking place through this unfinned area via the mode of convection, and that can be simply calculated from this formula, that is here referred as Q, or the heat transfer for the unfinned base, as H into area of unfinned base into TB minus T infinite. Okay, now the question is, we know this H and it is 9.5. We know TB, it is at 75 degrees Celsius. We know T infinite, which is at 20 degrees Celsius. Now the question comes, how do you calculate this unfinned area? So this is very simple geometry. You just need to understand what is the total area of the base. First you calculate the total area of the base, then you subtract the area of the fins from it, then you will get the unfinned area. Very simple geometry. Suppose are if you are told to calculate the unfinned area, then what you will do, you will simply calculate this area, this total area you will calculate first, then you will subtract this area. That is what we are trying to do here. This is exactly you will do, but instead of a single fin, there are 20 fins. So if you are trying to find out the unfinned base area, then first of all you need to find the base area, which is pi d0 L. L is already given as 1.2. We know d0 as 50 millimeter. So this is my total area, and now we need to subtract the fin area from it. So how many fins are present here? There are 20. So 20 into area of each fin. So how do we calculate the area of each fin? This is the length. First of all, you need to multiply the length and the thickness of the fin. This is very simple. So the area of a fin is dependent on the length of the fin, which is 1.2 meter, and the thickness is 2.5 millimeters. So we need to simply 2.5 millimeters, we need to convert it into meter. So we multiply this 10 to the power minus 3 factor. So now we have with us the area of unfinned base. So we just need to replace the values of this data here. What is d0? It is 50 millimeter. So we can write 0.05. Very simple. I think you are understanding how we can get this 0.05. Very simple thing to understand. So now we have the diameter, and what is the length? The length is simply what we have already used. If you remember, while calculating the heat transfer without fin, we had used this total surface area, and from this, after doing the relevant calculations, we will find that the area of unfinned base, that means the area where the fins are not attached, becomes 0.1284 meter square. So this is our thing. So why we are trying to calculate the heat transfer of this unfinned base? Because whenever you understand that a fin is attached here, you need to do this thing. You need to calculate the heat transfer from this unfinned base, and you also need to calculate the heat transfer from this fin. So then you need to sum it up so that you can find the total heat transfer from this surface. So one heat transfer is because of the extended surfaces or the fins, and the other heat transfer is taking place because of the unfinned base area, which was already present, but because of the attached fins, the unfinned base area is getting reduced. Okay, so after we have found out the area of unfinned base, it becomes a quite easy problem to calculate the heat transfer rate from this unfinned base, because you know H, you know AUB, or the area of unfinned base, and you know this temperature difference. Okay, and you will find that this becomes 67.09 watts. Okay, so this calculation should be done by yourself only. So the heat transfer through this area of unfinned base becomes 67.09 watts. Okay, so I will now remove this drawing because it will be not required. Okay, so I am just removing this drawing because I need space to write down this information which will be required while solving the final problem. So Q, I'm just simply writing UB, that means heat transferred through the unfinned base area, is found to be 67.09 watts. Okay, now we need to find out the heat transfer through the 20 steel fins which they are attached. Okay, so now we need to find out the heat transfer through the fins which is attached. Okay, so now the question is, we know this formula, we have already derived this formula for fins when the tip is insulated. This is the formula to calculate the heat transfer rate. Now for 20 fins we need to multiply it by 20. Very simple thing. Now try to find out what are the information that is not available to us. We know H, we don't know perimeter. Okay, we don't know perimeter. So perimeter is unknown to us. We do know the thermal conductivity. We don't know the area of fin. Or do you know? Yes, we have known, because we have already used the area of fin, but we don't have a recorded data for the area of fin, so we need to calculate it once again so that it can be easily done. So we don't know the perimeter, we don't know the area of the fin, and we don't know what is this value of this m, because we need to calculate it by the tan hyperbolic of ml. So we don't know what is the value of m, we don't know what is the value of m. Except these three data, all other data is available to us. So now we will try to find out these three data. Okay, so here you can find that I have done all the calculations, and now I will explain how we have done it. So area of the fin depends on the length of the fin and thickness of the fin. Okay, so you just need to multiply the length of the fin and the thickness in meters. We find that area of the fin becomes 0.003 meter square. The perimeter also depends on these two factors, but since there are two surfaces, we need to multiply it by 2. If you remember the previous classes, you will understand what do you mean by perimeter of a fin. So we find the perimeter of the fin as 2.405 millimeter, and this m is always referred as hp by kaf, k into area of the fin, and after putting the relevant values we will get m as 11.77. Okay, so after doing this we have all the data available with us, and now we can easily calculate this qf. Okay, this qf suggests the q heat transfer rate through this fin which is having an insulated tip. So after putting the relevant values in this equation and multiplying it by 20, because we need to calculate the heat transfer rate for the 20 steel fins which is attached here, and you will find that this calculation will yield the value of 937.75 watts. So the total heat transfer with the presence of fins, it simply becomes 67.09 plus 937.75. so the heat transfer rate with fins, I am just using this W to suggest. Okay, I will write WF with fins becomes 67.09. Okay, I will not write 67.09, I will just simply write QUB plus QF. That means we can find out the addition of these two factors, that's 67. So with the application of fins, we can see that the total heat transfer rate becomes 1004.84. That is almost 10 times than the heat transfer rate when there was no fin present. Okay, so this is why fins are used practically to increase the heat transfer rate. And here for this practical problem, we can see that the heat transfer rate is getting increased almost by 10 to 11 times. So this is huge increase. Okay, so with this understanding we will be moving on to another problem. Okay, so in this problem the concept was to find out the area of the unfinned base and the heat transfer rate through this unfinned base area and the heat transfer rate through the fins. So after adding up these two heat transfer rates, we find out the total heat transfer from the tube with the presence of the fins. So let us move on to the problem number 2. to clear our doubts and to observe the second case where we have taken the fins will have heat convection at the tip. That means that the fins will not be insulated. They will exchange heat in the form of convection with the surroundings. Okay, so let us see the second case here. So just let us read the problem here. A cylinder 5 centimeter in diameter and 1 meter long is provided with 10 longitudinal straight fins of material having thermal conductivity 120 watt per meter degree. The fins are 0.7 millimeter thick and protrude 12.5 millimeter from the cylinder surface. The system is placed in an atmosphere at 40 degrees Celsius and the heat transfer coefficient from the cylinder and fins to ambient air is 20 watt per meter square degree. If the surface temperature of the cylinder is 150 degrees Celsius, calculate the rate of heat transfer at the end of the fins. So that means we are talking about the fins where heat convection is going on at the tip of the fins. Okay, so we must remember the third case where we had taken the fins of finite length with heat convection at the tip of the fins. So this is the formula. This formula is huge. I understand this is impossible for you. This is quite impossible for you to remember this kind of formula. But the suggestion is that you must start from the boundary conditions. You have the basic temperature distribution, that is equal to theta is equal to C1 into e to the power mx plus C2 into e to the power minus mx. So from this equation we have two boundary conditions. The first boundary condition being at x equal to 0, theta is equal to theta b. That means at base the temperature is equal to theta b. So from that boundary condition you can start with, and for the second boundary condition the heat transfer rate via the conduction should be equal to the heat convection transfer rate. Okay, so at steady state the conduction heat transfer rate equals to the convection heat transfer rate from the tip of the fin. So from the help of two boundary conditions you should derive this heat transfer rate, or there is always way if you can remember this. But still if you are not interested in remembering this formula, this huge formula, then you can always start from the basic, from the fundamental, so that you can arrive at this formula and you can do the relevant calculations. Okay, okay, so let us start what the problem is saying. So you have a cylinder. Some portion of the cylinder, the outer surface of the cylinder is finned and some portion is always unfinned. So you need to calculate the heat transfer rate through this finned portion and the heat transfer rate for the unfinned portion. Okay, for the unfinned portion it is very simple. You just need to calculate the area of this unfinned base area. This AUB suggests that the area of the unfinned base, and you just need to do this little bit of convection formula use, so that you can find out the area of so that you can find out the heat transfer rate through this unfinned base area. Okay, so our job is to find these two, that means heat transfer rate through the fins and through the unfinned portion, and then we need to just add it up, so the net heat transfer rate from this outer surface of the cylinder can be calculated. Okay, so what we will do, we will find out this individual data and we will go on for the calculations. Okay, so let us start with K. We know this K, this thermal conductivity is very much known to us. So let us find out the area of the fin. So how we can find out the area of the fin? If you remember the previous problem, then it becomes very easy. You know, you need to multiply the length of the fin and the thickness of the fin. So 0.75, but the unit is in millimeter. So you need to multiply it by 10 to the power minus 3. Okay, so now you have thickness in meters, and just try to find out the length of the fin. What will be the length of the fin? It is here in this problem it is uh, defined in a little different way. It is already told as 1 meter long, so you can say the length of the fin, or the cross section, or the cross sectional area of the rectangular fin should be multiplied this one, so that you can find the area of the fin. Now let us find out this m. Okay, what is this m? If you remember, m is a constant which we have taken arbitrarily. It refers to the hp by kf. We have h we have h as 20 watt per meter square degree. We have k as 120 watt per meter degree. We have area of the fin as 0.75 in 10 to the power minus 3, but we don't have the perimeter. So how we can calculate the perimeter? It is again simple. It is again very simple. It is calculated by this formula, b plus h, right? The breadth. Now the breadth is 1 here, but this height of the fin, or the thickness of the fin, is very less compared to this breadth. So what we can do, we can assume that this perimeter equals to this twice of the breadth, which is here 1. Okay, so we will assume this perimeter as 2 meters. Okay, this height would have been 0.00075. Okay, and this breadth was 1, so we can neglect that 0.0075 part. Okay, and we are taking this only one, the breadth value, that is 1 here. So the perimeter becomes 2, and now we have all the data with us, and we can find that this m would become, after putting all the relevant values, you will find that this m would become 21.08 meter inverse. So the value of m would become 21.08 meter inverse. Very simple thing to understand. So this would become 21.08 meter inverse. So now we have this. We know the temperature of the base. We can easily understand the temperature of the base is 150 degrees Celsius. We know the ambient air temperature, the surroundings temperature, that is 20. But we have to calculate these values. Okay, this h by km, this tan h of ml, that is tan hyperbolic function of ml. So we will just do these calculations. So how you can calculate this tan hyperbolic of ml? If you remember cos and sine, then it would be simply defined as sine hyperbolic of ml divided by cos hyperbolic of ml. So that is e to the power ml plus, I'm sorry, in case of sine it should be negative sign, e to the power minus ml divided by e to the power ml plus e to the power minus ml. Okay, so there would have been by 2 factors, but since in both sine and cos, both sine hyperbolic and cos hyperbolic, there is by 2 factor, so this factor gets reduced, and ultimately you are left with these values. So you know the value of m, you know the value of l, that is 1 meter. So now you can find out with these calculations, and you will find that it would become, you can also find it through the calculators. If you know this value of ml, this ml would be actually, if you do the calculations, you will find that this ml would be 0.2635, right? Very simple. So you have m and you have l with you. So l here, please consider that this l here refers to the length of the fin that is protruding from the cylinder. Okay, that means here you have to consider this l as 12.5 millimeter. Okay, you must remember it or understand it. This l should be considered as 12.55 millimeter. So please refer to the diagram that we had used for describing the heat transfer mechanism. through the fins, then it will be easily understood, I hope. Okay, so this L would become 12.5 millimeter, and ultimately you will get this ml value as 0.2635. And if you are interested to find out the hyperbolic function of tan hyperbolic function of ml, you will find that this function would become 0.2576. So now you can see that all over the screen we have some data which we have just calculated. We have m, we have m, we have af, we know k, that is 120 watt per meter degree. We know tb minus t infinite would be 120 minus 40 degree, that would be 80. Okay, so sorry, it would be 150 minus 40, I'm very sorry, it will be 110 degree Celsius. You know the tan hyperbolic of ml, that is 0.2576. You know h by km as 0.007906. So we have done these calculations, and after putting all the relevant values, you will find that this function would become it will be becoming 55.29 watt per fin. Okay, so I will just remove this because this is causing a little bit of trouble here. So it becomes 55.29 per fin. It becomes 55.29 per fin. So we have 10 fins. Okay, so for the 10 fins it would be 550. Okay, very simple, it would be 552.9, right? So it would be 552.9. so let us just write it, 552.9. so I will just remove this per fin part, and we will be finding out that the heat transfer through the 10 fins which are placed over the cylinder, that is 552.9 watts. Now the question is, what is the heat transfer through the unfinned portion? We need to find out that, because to calculate the total heat transfer we need to understand what is the heat transfer through these fins and what is the heat transfer through the unfinned base portion. So we need to find out this, and to find that we need to calculate the area of the unfinned base. And how this unfinned base can be calculated? We know this is very simple. This is pi h pi g, it is h pi d. Okay, I'm very sorry that I have written 2 pi over here. So it will be pi into d into L. Okay, so it will be pi into d into L minus AF, that is the area of the fins, into 10. Okay, because we have 10 fins which is attached in this cylinder, so it will be 10 fins. Okay, so this is our question here. So now this diameter, so if you put this diameter as 5 centimeter and this L as 1 meter, so you will find that this would become this will reach the value of, so the area of the unfinned base would become 0.1495. This D is nothing but this 5 centimeter and this L is 1 meter. So after doing the calculations, you will find the area of the unfinned base portion would be 0.1495 meter square. And after receiving this value, you can simply go on through this formula and go through this formula, and you just find out the heat transfer through the unfinned base portion as 328.9 watts. And now what is your initial thing? You just need to add it up. So ultimately you get, this is your heat transfer. So the total heat transfer at the end of the fins is 881.8 watt. Okay, so I think we have calculated the heat transfer rate. Sometimes an additional question can be asked to you, if what will be the temperature at the end of the fin. So you just need to follow the simple temperature distribution equation that we had derived for the fins, which is undergoing convection at the tip of the tip. So with the help of that formula, you can also calculate the temperature distribution at the end of this fin. Okay, so I think we have discussed two specific problems regarding the two specific cases um, of the two specific boundary conditions. So I think till now we will end our lecture. Today we will end our lecture, and in the next lecture we shall discuss about the performance of fins. Okay, we shall discuss the effectiveness and the efficiency of the fins, and we'll also take some numerical problems regarding the efficiency and the effectiveness of the extended surfaces or the fins. So till then, goodbye and thank you very much.